In section 4.3, question number 1. So you you could do it using the table, all the information that I did before. In fact, maybe it'd be helpful. What if I just write it again? So how do you find, or I'll just do the vertical. How do you find vertical asymptote? Step 1, factor and reduce. This fraction doesn't need to be, there's nothing to factor on this one. There usually isn't. Step 2, denominator cannot, I'm doing the, what am I doing? Denominator equals 0. Yeah, so the denominator equals 0. So so this one, pretty easy. You can tell grab that denominator. What makes this denominator equal 0? Either part, huh? Two things are timesing to be 0. Either part could be 0 to make that happen. Yeah, so the x alone could be 0, or the x plus 11 could be 0, and move that over, which means minus 11, huh? So x could be 0 or minus 11. And what that means on the graph, I think you know, is that there would be back here at negative 11, and at 0, there would be vertical asymptotes, huh? And what does a graph do at a vertical asymptote? It doesn't touch it, for sure. Yeah, you cannot touch a vertical asymptote. The graph never touches the vertical asymptote. What does it do when it gets close to it? Yeah, it's right. As it gets close to it, as it gets close, it rockets up really close to it, or maybe down. It just depends whether it's positive or negative. And then these guys, same kind of thing. Maybe it'll go here, and I don't know exactly, to tell you the truth, but I know it's going to get super close. At vertical asymptotes, it either rockets up to infinity or down to negative infinity. And it gets closer and closer to them forever. That's what always happens at vertical asymptotes. Now, why? Why does that happen? I think it would be valuable, especially if you're going to move on into calculus next semester, to know the reason why. Like, why does a function actually do that at a vertical asymptote? Yeah, it's because we're dividing by 0. Yes, let me make sure that's clear. Do you realize that when you divide by 0, the number goes towards infinity? I think it's valuable to actually fool around with numbers every now and then. So if you take 100 over 20, what I'm going to do is I'm going to give an example where I just keep the top the same and I just keep lowering the bottom. So what's 100 divided by 20? 5. What's 100 divided by 10? 10. What's 100 divided by 5?
20.
Yeah, 5 goes into 100 20 times. 10 goes into 100 10 times. 20 goes into 100 5 times. See how the answers are getting bigger and bigger and bigger as the bottoms get smaller and smaller and smaller? Because that bottom will then, a smaller bottom will go into the same top more times, won't it? Keep going. 100 over 1. How many times does 1 go into 100? Well, you know it's 100. And now can you get smaller than 1? Yeah, you could get like 0.1. Right? That's like 0.10. Like, think about money, like 10 cents. How many dimes in $100? 1,000, huh? Because there's 10 dimes in $1 times $100. That'd be 1,000 now. See how it's still getting bigger? And then what if I take 100 and I divide by 0.01? How many pennies in $100? 100 pennies in every dollar times $100, huh? Be 10,000. So anyway, you see how the number, as the bottom heads towards 0. See how the bottom is going closer and closer to 0? Right? The bottom has become 0.01. I could even get smaller. I could make it 0.001. How many times is that going? Well, that would be 100,000. See how it's getting, the answer is getting bigger and bigger and bigger. So as the bottom goes towards 0 and the top stays fixed, the overall fraction heads to infinity. Do you feel that? See how that's actually happening? So that's what happens at a vertical asymptote. The bottom gets closer and closer to 0. Let's go back and look. Meaning, as x gets really close to negative 11, like negative 10.99, if you plug in negative 10.99 for x, that's really close, right about here, huh? Super close to 11, then this will be super close to 0, because 11 minus 10.99 will be 0.01, won't it? Really close to 0. So that bottom will get really close to 0, and now you might say, yeah, but what about the other part? Well, if two things are timesing each other, if one part is basically 0, then 0 times whatever, the whole thing is basically 0, right? So as either one of these gets really close to 0, so that would be as this part gets like 0.01, as x gets really close to 0 there, or as this x gets really close to negative 11, either way, the bottom gets close to 0, and that's why the function goes rocketing up to infinity, up or down to negative infinity, depending on whether the sign's positive or negative. Does that make sense on that? That's why that happens on a graph. That's what makes that happen. That's why we look where the bottom is 0. Because when the bottom is 0, dividing by 0, 0 goes into the top, or something that's almost 0 goes into the top, just like these guys. Something that's almost 0 goes into the top infinite times. It heads towards infinity. The closer the bottom gets to 0, the closer the division gets to infinity, right? Okay, so that's the reason why we look for vertical asymptotes where the bottom is 0. That makes the answer go up to infinity. Dividing by 0 is basically infinity. Now, let's do the other part, horizontal asymptotes. How do we do that? Well, to do that, let's take this function. We're still doing number 1, and that was, what was it, x plus 5 or, oops, x plus 5 over x times x plus 11, yeah. Let me go ahead and, for purposes of part C, which is the horizontal or diagonal asymptote, let me go ahead and multiply out the bottom. That'll be more useful. And so I get x plus 5 over x squared plus 11x. Okay, so now why that whole set of rules for it? In fact, let me just write out the rules again, super quick for you. For the horizontal diagonal, case 1, we said if the denominator is bigger, then it's a horizontal asymptote y equals 0. Let's start with that one. Why? Well, horizontal asymptotes are all about what happens way off to the right. So let me put one in here. So we're wondering, like, as the function goes way, way off to the right, does it like level off at some level? We're not really concerned, when we talk about horizontal asymptotes, we're not really concerned with what it does around here. It can do whatever, who cares? We're concerned about way off to the right and way off to the left. That's why you can cross, did we talk about that last time? I think we did, maybe. That's why you can cross a horizontal asymptote a bunch of times. Doesn't really matter at all. It's not a problem. Whereas you can't cross a vertical, can you? Right? You never touch a vertical, because that makes the bottom 0, and that's not a number. That's infinity. But horizontal, you can totally cross, around the middle between negative 10 and positive 10. Whatever. Who cares? Horizontal asymptotes don't matter to us at all. They're what happens way down the line, right or left. Way out there. Does it eventually level off or something like that? That's what we're wondering. So in other words, we're talking about plugging in things way off to the right. Numbers like 100 or even bigger, 1,000 or, a million. We're talking about, x going way off to the right, 10, 100, 100,000, a million, a billion, a trillion. What's going to happen? So can you imagine with me, if I took this very one we're looking at here, and I plugged in like a million right there. Well, let me just plug in 1,000. Well, no, let me plug in a million. I just want the immediate powerful effect. If I plugged in a million there and there. Now, I don't know what the number is, but I want you to kind of feel it with me. It'd be a million plus 5. See how that 5 is just like, who cares, right? A million plus 5. The 5 is just nothing. Do you see how the lower power terms become irrelevant? Let's look at the bottom as well. Here we're going to have 1,000,000 squared. What's that? That's 1,000,000 times 1,000,000, isn't it?
A million.
That's 1,000,000 millions. What's 1,000,000 millions?
Couple billion.
It's a trillion.
Oh, sure.
We're talking national debt numbers. It's a trillion. 1,000,000 millions. Because you just would add 6 more zeros. Anyway, plus 11 times 1,000,000. Do you see how even that is nothing?
19.
Now when you think, whoa, no, come on, Mr. 11 million. What do you mean that's nothing? Well, it's nothing compared to a trillion. Do you see what I'm saying? It's all relative, right? Like national debt, sadly. If you got $1 trillion, 11 million doesn't even hardly begin to touch it. Why not? Because that's 1,000,000 millions, and that's only 11 millions. It's like way smaller. 1,000,000 millions. If you have 1,000,000 millions, you don't care about losing 11 millions, right? It's just not even on the radar. It's just a blip, right? In comparison, and I'm only at 1,000,000. We're going to go to the right forever. We're going to go to a billion and a trillion. I can plug a trillion in there, and this would be a trillion trillions, and this would still just be 11 trillions. So you see how the less powerful terms are becoming irrelevant as you go to the right or left, negative million, same thing, forever. Get that idea? As far as if we're wondering, well, what's this function going to do? As we go to the right forever, what's he going to do? Is he going to go up? Is he going to go down? What's he going to do like way off to the right and the left? Well, if you want to know that, it's actually pretty easy to figure that out. Because the details, the smaller players don't matter. This guy is irrelevant and this guy is irrelevant. Okay, so what does that mean? That means it effectively becomes x over x squared when you're way off to the right or way off to the left. That's why we say, like in the rule I gave you, all that matters is the denominator and numerator power. Do you see how the power on the top and the power on the bottom is all that really matters? The smaller players don't matter when you're going way off to the right, okay? Now, what would you do with that? How do you reduce that? Like somebody said, I've got x over x squared. You would reduce that to be 1 over x, huh? You'd cancel. And that's right, okay? And now, okay, and what's that? Well, remember where we're going. X is going off to 100, 1,000, a million, a billion, a trillion. So basically, X is going to, let's just plug in 1,000,000 again. So now I'm plugging in 1,000,000. I hope I'm not confusing you. Here, let me go one more time. So the original function was, I want you to really understand this, x plus 5 over x squared plus 11x. Okay, and remember, I'm letting x head towards 1,000,000 and beyond, right? I'm letting x be 1,000,000. In what we're doing right now is actually valuable thinking for calculus. Right away, if you're going to calculus 1 will, like chapter 2, like right off the bat, we'll start off, and they'll write it this way. That's the I'm not going to write that. That's the calculus lingo. But they'll say the limit, which is like a heading, as x heads towards infinity. That's what we're doing right now, basically. I'm getting your thinking moving that way. I'm saying what happens as you go way off to the right. So they'll take a function like this, and they'll say, what's going to happen to this function? What's the limit? They'll put a limit up here in front of it. And they'll say, what's the limit of this function as x heads towards infinity? So we've already seen that as you plug in really, really big numbers, this guy and this guy are just irrelevantly small compared to the main. So the most powerful term on the top and the most powerful term on the bottom are really all that's going to matter as you go off to the right forever, okay? So we're here, and then that's reducible to here, isn't it? So really the function has become effectively that, as x heads towards infinity, 1,000,000, a billion, a trillion. Okay, so what's that? Well, put in your million now. Remember, again, x is headed to huge numbers, million, billion, trillion. So what is that? Try to be real with it. Let me try to make it real. What if I said, last night, I was hungry, so I had some pie. I had 1/1,000,000th of the pie.
You're almost nothing.
It's almost nothing, isn't it?
It's a micrometer.
That's just the smell of the pie, right? That's like the smallest of crumbs. That's 0. Yes, it's sad to not have pie when it's there. Yes. So it's basically 0. That was our rule, right? See how the denominator power was bigger than the numerator power? Remember me talking about the tug of war they have? And so you see the bottom is more powerful. And so when you plug 1,000,000 in for x everywhere, the bottom's going to be 1,000,000 millions. He's going to dominate. He's so much bigger that the fraction reduces to 1 over x effectively, which means 1,000,000th, which is nothing. Y equals 0. Let's go back to our rule. That's what we said when the denominator is bigger, you get a horizontal asymptote, y equals 0. What does that mean? That means that this function, as you go to the right forever, it's going to flatten out at 0. It's going to come down like this. Or maybe from the bottom, I don't know. I don't know, bottom or top, whatever. It's going to head towards a height of 0 as you go to the right forever. Eventually, I mean, it might do whatever in between, but eventually it's going to get closer and closer, right and left forever, to a height of 0. That's its limit, we say, in calculus. The limit of that function. Get that idea? So that's where that can, let's do, that was case 1. Let's go to case 2 now. So our answer to this problem then would be horizontal asymptote. So that is the answer to question 1. Horizontal asymptote y equals 0 because the bottom is more powerful. So you head off to the right forever. He'll dominate. He'll bring the graph down, flatten it to be 1,000,000th, which is 0. Now, let's do another case. What if you had something like 3x plus 5x squared minus 72 over, I don't know, 86 minus 12x minus 7x squared. Okay, same kind of thing. I'm just making up a problem here. And I'm going to let x head towards infinitum, basically doing the limits, what you'll call it in calculus. So x equals 1,000,000. Again, think about, I'm just jumping right to the horizontal case now. So horizontal or diagonal. So what happens as you go right or left forever on a graph? Well, if you're going to plug in 1,000,000 for x here and here and here and here, do you see that this guy, this guy, this guy, and this guy are irrelevant? The highest power term is so much bigger. This, again, is 1,000,000 millions, way more than 12 millions. So that it's going to become only, all that will matter effectively is those two terms. Again, that's why in the table we just talk about the d and the n. The numerator and denominator powers are all that matters, okay? So it'll effectively become that. As you go far enough to the right and far enough to the left, those are the only ones that will really affect anything or matter. And then what can we do with that? Can we reduce that? Yeah. Those cancel. And so it's just minus 5/7. Now, so that means that's what it's going to look like as you go to the right or the left forever. Now, what is that? Notice that doesn't have an x. There's not an x there, so that's not a slope. That's another flat line. It's just at a height of minus 5/7, right? So graphically, let me draw a little graph here. It would mean at negative 5, what is that? Like if this is -1, this is -2, it's about right here. It's almost 1. So at a height of negative 5/7, the graph will eventually flatten out. I don't know, whatever, blah, blah, blah in here, but it'll eventually flatten out and eventually flatten out at a height of negative 5/7, eventually to the right and the left. Does that make sense? That was our case 2, wasn't it? Remember case 2? If the denominator power equals the numerator power, see they're equal, then it's just y equals a over b, where the a and the b are the numbers. This is the a and the b in the front of those most powerful terms. It's another horizontal asymptote. That's how we came up with that case 2. Case 3. We good with that? Case 3. What if you have something like, let's say 3x squared minus 7x plus 5 or whatever over 12 minus 17x. Okay, so again, we're saying as you go to the right forever, x is 1,000,000. X is heading to the right forever or left forever. Plugging that in, what's going to happen? He doesn't matter, he doesn't matter, he doesn't matter, huh? Just, they'll be so small in comparison. So it'll be 3x squared over minus 17x, effectively. Should go right or left forever. And then we can reduce that. That's going to equal 3x over minus 17, huh? All right, just cancel this with this. So what is that? Well, that is a slope now. That's like an mx plus b kind of thing, isn't it? That we have an x there now. That's a slope. So that is a diagonal line. It's not a flat line. It has a slope. It's not flat. See, it's not like the last one, which was just a number because the x's were the same power. So they canceled out. So we just had a number, which is a flat line. No x. Now we had the top was 1 power higher than the bottom. So we do have a leftover x, which means that's a slope. That's an mx plus b. That's a diagonal line. We call that the oblique asymptote. That's case 3, when the numerator is greater than the denominator by 1. See, the top power bigger than the bottom by 1. That's going to be a diagonal line. Now, how you find that diagonal line is a little tricky. Long division, I'll show you that when we get to the homework in just a minute. But for now, I want you to know that that's a diagonal line, which means on the graph, as you go off to the right forever, there's going to be some diagonal line. This would be actually a negative sloped one, wouldn't it? There's going to be some negative sloped, in this case, it's a negative there. Negative sloped, so it's going to go whatever, blah, 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 but then eventually, it's going to approach that diagonal line. It's going to head off to infinity in diagonal fashion. Negative infinity and positive infinity in diagonal fashion. Not flat, but diagonal. We call that an oblique asymptote, diagonal asymptote. Last case, case 4. So y equals something like 17x plus 2x to the 9th over, 3 minus 12x to the 4th. Okay, so, well, here, let's just make this 7. Okay, so again, we're, x is headed towards infinity, right? It's a limit, basically. We're going way to the right or way to the left. So what does that mean? He doesn't matter, he doesn't matter. So effectively, this is going to be 2x to the 9th over minus 12x to the 7th. Reduce that. That's going to be minus 1/6 x squared, isn't it? Right, 9 minus 7 on the powers there. So that means as x goes to the right forever, as we're going way over here on the axis, way to the right or left forever, it's going to head off in what fashion? What is that? That's not a diagonal line. That's not a flat line. What is that? That's a parabola. That's a U-shape. You guys know that x squared is a U-shape. So that's going to head off to the right forever, and that's an upside down, the negative there, huh? That's like an upside down U-shape, isn't it? That's an upside down parabola. So what does that mean? That means the so that's the well, I'm not. That should be my dot. I didn't make that dotted. Let me dot that. Let me try again. So that's going to be my asymptote curve. Now, we don't have an asymptote curve. You could. Math could have done. I mean, there does exist such a thing. That is what that function will do. That is a guideline for that graph. We're just not going to go there, though. We're just going to say, hey, it's not flat. It's not diagonal. We don't care what it is then. But I'm telling you what it is because I want to give you understanding and not just rules. That is right. So now the graph will go, whatever, but eventually, off to the right forever, it will start hugging that curve. It'll get closer and closer. That curve will serve as a guide curve to it. Same thing on the other side. It will eventually conform to that curve. If you go far enough right, far enough left, that curve will become the guideline for it. So anyway, we don't care. We just say, hey, look, case 4, if the numerator is bigger than the denominator by 2 or more, then that means, what if it was more? What if this was 10? Or how about 11? Then you'd have a 4th power. Or 12, you'd have a 5th power. Who cares? It's some kind of a curve. So we're just going to say it's going to head off to the right and left forever in some sort of curved fashion. Rocketing up forever or rocketing down forever. We don't care. It's just not a line. It's not a flat line. It's not a diagonal line. It's some kind of curvy thing. And we're just going to say, no, it's not horizontal. It's not diagonal. We're done. There's the reasons why. Does that make sense on that? So let's dive into the homework, especially we need to see how to do that long division. Okay, so let's do number 6. The the first thing we do on number 6 is they ask you for the domain. You know, they're going to go through all that kind of stuff again. So it'll be pretty easy for you at this point, I think. So what would be the domain of that one?
6.
Yeah, just x can't be 6, huh? Right. Does that make the bottom 0? Not allowed. Okay. What's the vertical asymptote? Same thing, huh? Those are the same. At 6, you're going to have a vertical asymptote. That's why you can't go there. All right, now, on to part C. On to part C. So remember again, I gave the rules for the horizontal, diagonal asymptotes. Let me write them up here again real quick. So, case 1, if the denominator is bigger, and it doesn't matter by how much. If the bottom is bigger, then it's a horizontal y equals 0. If they're equal, then it's also a horizontal, but it's a over b. It's not 0. And if the numerator, so the weird case, is if the numerator is bigger by 1, then it's a diagonal. And how you find it is long divide the denom into the numerator, and up here you'll get your mx plus b as the answer to the long division. And I'll show that now on this problem. And then case 4, if the numerator is bigger than the denominator by 2 or more, then that just means no horizontal, no diagonal, because it actually heads off in a curved fashion. No horizontal, no diagonal, what they call oblique. All right, so there's the rules, which we've seen the reason. By the way, do you see how much better it is to understand than to have rules in math? And that's really the way you want to try to do all of math and science. It's just, it's just hard to remember all these rules, huh? Especially imagine trying to remember these, a couple months. This is a long, we have 18-week semesters here. This is long. I went to school at Cal Poly where they had 10-week quarters. Those were kind of nice. You got in a class you didn't like, it was over pretty quick. 10 weeks, boom, boom, it's over. So these 18-week semesters are long. So into the 18 weeks, it'll be Christmas time. The weather will be cold, and we won't be fanning ourselves. It'll be cold. It'll be nice. And but who's going to remember all these rules 2 months from now? I mean, you can write them on your final sheet. But still, whereas the understanding will take you further, huh? And I think it's more interesting, too. There's reasons for things. Okay, anyway, so now with understanding, look at this function. We're going to try to find the horizontal or diagonal asymptotes. So we're talking about plugging in, letting x head towards infinity, right? It means way off to the right. So all that's going to matter is this and this, huh? As you go way off to the right or the left. So you're going to get x squared over x, and that's just x. Now hold on, though. This is where I want to help you see. That's not, that indicates it's diagonal. Yes, that does mean, okay, it's diagonal. But that's not the exact answer. You're going to have to actually long divide to find out what it really is. It's going to turn out to be x plus 8, I think it is.
X plus 8, yeah.
Yeah, it's not just x. So everybody hearing me on that. When you divide and you get that x to the first power, that does tell you, oh yeah, that's like mx plus b. That's like mx plus b. So it is diagonal. That's a diagonal line, right? Not a flat line. Whenever you have x, it's not flat. If you just have a number, that'd be flat. If these powers were the same, if it was x squared over x squared, that would just be 1. That'd be a flat asymptote. This is a diagonal because it's mx plus b. But that just tells you it's diagonal. That doesn't tell you what its equation is. So now to find the equation, as it says here, you have to long divide the denominator into the numerator, and the mx plus b will be the answer to the long division. So let's do that now. So this has to go into that. So let me go back. So y equals x squared plus 2x minus 24 over x minus 6, right? Yeah. So now to find the diagonal line equation, I'm going to long divide x minus 6 into x squared plus 2x minus 24. Got a long divide. Now, why? Now I'm trying to leave no stone unturned today, trying to make sure I give all the reasons why everything's true. Why long division? Well, think about just normal fractions. If you have something like, how about 8 over 3? How could you? What's another form you could turn? Can you turn that into a what's it called? Mixed number, right? How do you do that? Bottom into the top. You long divide, huh? That's how you turn it into a mixed number. 3 goes into 8 twice. 2 times 3, 6. Subtract 2. And what do you do with that 2? It's 2. And this goes over that. Remember, it's bottom over left, like that. Yeah, so this and this are two different ways to say the same thing, aren't they? Improper fraction or mixed number. Well, that's what we want to do here. Instead, right now, this is like an improper fraction. Why is it an improper fraction? Power in the top is bigger than the power in the bottom. Like number on the top is bigger than the number on the bottom. It's an improper polynomial fraction is what it is. And so we want to turn it into a mixed number polynomial fraction. Now, as we do that, let me preempt a question that's probably going to come to your mind. When I write 2 and 2/3 like that, with no symbol in the middle between the 2 and the 2/3, what does that really mean? Does that mean 2 plus 2/3, or does that mean 2 times 2/3?
2 plus.
2 plus 2/3 of a whole.
Yeah, so what you want to do, when you're answering math questions like this, you want to try to be as real as you can. That'll go such a long way. Really, if I was, after all these 25 years, I think I qualify as a little bit of an expert on how people think mathematically. I've taught thousands of students over 25 years and watched how people think and raised my own 5 kids and homeschooled and watched, and they were all a little different in the way they thought. What I've noticed, if I was to give one sentence on what, some people say, I'm a math person or I'm not a math person, or I seem to have that, some people seem to have that radar sense of what to do with math and some don't. The number one thing I've noticed is the people that have that radar sense, math is more real to them. So if you strive to make it more real for yourself, rather than just symbols on a page, just moving around in random rules, it'll help you. That's that radar. The radar for people that are dialing in, it's real to them. So when they look at 2 and 2/3, they don't just see symbols and think about some rule they learned in some math class. They think 2 and 2/3 pies. I'm always doing pie. Huh? I got to do something else here. I don't know what else you could do. Anyway, what do you got? Cake. Oh, man, that's a big change there. 2 and 2/3 cakes. Whatever. 2 and 2/3 of something, right? 2 and 2/3 pies. What does that mean in real life? So I've got in my cupboards at home 2 and 2/3 pies. Does that mean I have 2 plus I have 2/3? Or does that mean I have 2/3 2 times? Yeah, it means the plus, doesn't it? We all know that as soon as we get real with it. That's your best guide in math. It really is to make it real. You'll know. So yeah, it means plus. So that's kind of weird, isn't it? I think it's weird of math that they did this way. There's no normally when there's no symbol in the middle, we're always trained to think it means multiply. Well, there's an exception here, and math isn't perfect. It's bad notation. So we got to be careful here. They kind of messed up the notation. Yeah, it really means add, doesn't it? So when I go to, and the reason I'm telling you all that is because when we do complete our long division here in a second, we're going to need to remember that when you actually write it with X's, you're going to need to put in the plus sign. Because that's what the mixed number thing really means, we now see. All right, here we go. Let's do the long division. So we're gonna change the form. So how do we do long division with letters? Kind of a tedious thing. Let me remind you what you would do with numbers. I mean, we just did one there, but let's do one a little bigger. How about if I did 21 into 4, 3, 8? So think about what you would do with numbers, and then do the same thing with the letters. So what would you, first off, would you think about the whole thing? You wouldn't, would you? You wouldn't think about 400 and how many. You would just go into what you can go into, just the 43, huh? That's exactly what we'll do over there. So you just go 21 into 43. In fact, you'd probably mainly just look at the 2 and the 4, huh? And you'd say, what can I put up here times the 2 that'll match the 4? Or make the 4. Yeah, 2, right? And you'd go, okay, 2. Right? 2 times 2 makes the 4. Exactly right. And now when you do that, would you just write the 4 and nothing else?
No, 42.
No, you'd go to both of those. we'll need to do that also. And that'd be 42. Let's hold up there and go back and do the letters now. So you're going to put up here, you're going to say what times the front will match the front. It's exactly what we did here, right? Times the front, match it. So what times x makes x squared? X, huh? Yeah. So x. Now, when you write that x there, is it only going to go to the front one? No, remember it goes to both, doesn't it? So it's going to have to distribute to both of those two, isn't it? So it'll go to both. And so you'll get x squared and you'll get minus 6x. Good so far? It goes to both. Distributes to both. Okay, now, let's go back to the numbers. Now that you've done that, what are we supposed to do next?
Change the sign.
Subtract, huh? Yeah. We got to subtract this 42 and get 1. And then bring down the 8, right? Got to subtract. And I subtract both numbers. I don't like subtract the 4, but then add the 2 and write 5, do I? I subtract them both. So that negative affects both of them. We don't even think about it with numbers, but you agree with me? That's what's happening, huh? We're going to have to intentionally think about it with letters. So I'm going to subtract the entire bottom line, not just the front part. These guys cancel. Sure, that's right. But what happens in the other spot? Yeah, and I think it'll help you to put parentheses. You don't have to, but that's really what's happening. You're subtracting the whole bottom line, just like you subtracted the whole 42, huh? So that means it's minus a minus. It's actually going to add the 6x, going to get 8x, huh? All good there? You're subtracting that whole bottom line. Bring down the minus 24. All good? We're ready for another step. Now, over here, let's go back to the numbers. Over here, could we do another step? 21, 18. How many times does 21 go into 18?
It doesn't.
It doesn't. Now, of course, we could go add decimals and do a decimal thing, but if we don't want to go decimals, and we don't,
18 over 20.
then you'd be done here. Yeah, and you'd write your remainder, huh? You'd go bottom over left. You'd say 18 21s, which really means plus, as we talked about.
6 over 7.
Right, and you'd reduce that. Yeah. Right, we all good there? That's what you would do. Now, how do you know when you're done? When the bottom is lower than that. The divisor, it's called. Right? When the remainder is lower than the divisor, you're done. So how about us? How do you know? Now, what is lower in the x world? Lower power. Whatever is true of numbers in the number world is true of powers in the polynomial world. So, is this a lower power than this? No, they're the same. So we can do another step. They're the same. All right, so how do I do my next step? Well, you just look at front and front. Again, there's so much going on it can confuse your eyes. Just look at front and front. Just right here and right here. Don't worry about anything else in the world. Whatever you put up here times the front, that'll match the front. What's that going to be? 8. Going to be 8, huh? It's going to be plus 8. And that 8 will go to both. It's got to distribute. And you'll bring it over here. And it's going to be 8x minus 48. This was a 24 there. Good to there. Write that a little better. Okay. And now, what do I do now? Draw my lines, subtract. And I'll put parentheses to help me remember I'm subtracting all of that. Okay, so the 8x is canceled. Now, again, minus a minus 48. We'll actually add 48, won't it? 48 minus 48 is going to be 24, huh? Am I done there? Yeah, because this is a lower power than that, meaning it doesn't have any x at all. And that has an x. Even though the number 24 is bigger than 6 or 1 or whatever, it's not the in the letter world you care about power level. That's what is your level. So there's no x here at all. And that's lower than x. So that's our remainder. And so what have we learned you always do with a remainder?
You put it over x minus 6.
You add 24 over x minus 6. Yeah. Bottom over left. Right? It's exactly what we did with the numbers on that. Does that make sense? Because what? Because that x minus 6 has been the denominator all along, hasn't it? Right from the beginning, x minus 6 was the denominator. So whatever you have left at any stage could be put over x minus 6. This is all over x minus 6. So that's what remains. It's over x minus 6. Okay, so what have we done? What does all this mean? Let me erase all this side, which was just for our comparison. And let's think about what we have accomplished. So this all means that this entire fraction is equal to this x plus 8 plus 24 over x minus 6. That's what happens when you long divide, right? Like remember I started with, what did I start with? 8 over 3? I started with 8 over 3 and I said that's the same as 2 and 2/3, right? Two different ways to write that fraction, either as an improper fraction or as a mixed number. That's what we're doing in polynomial world right now. We're saying we have this fraction as an improper, and now we're writing it as a mixed polynomial. Why? Because the mixed polynomial form is easier for us to tell what happens now as x goes to infinity. So as x goes to infinity, this part's, this x plus 8, this part's going to infinity. Great, okay. This part's also going to infinity right here, isn't it? I'm almost there. I know it's been a long discussion. What's infinity minus 6?
Infinity.
6 less than infinity.
Yeah, it's basically infinity, right? So this part here is 24 over infinity. If I said, last night I ate 24 10/millionths of the pie. That's no pie again. Doesn't matter, that's a 24 on the top. 24 pieces out of 10 million pieces is the smallest crumb of the pie. If you break that pie into 10 million pieces, they're crumbs. And you eat 24 of them, it's just pie dust, right? So I basically ate no pie. This is headed towards 0, which means what? The remainder you don't need. The remainder is dust on the scales. It doesn't matter. It's not weighing in as anything. Since we're headed, don't lose context. We're headed to infinity. Yeah, in the middle, everything matters. But way off to the right, way off to the left, positive 10 million, negative 10 million, the remainder is irrelevant. It's just going to go to 0 because the bottom is a bigger power. It's going to be 24 over infinity. So really all we need is x plus 8. That's what this graph will look like as you head to the right and the left forever. So on a graph, what does that look like? That's up at 8. That's a vertical, what's it called? A y-intercept at 8. And the slope is 1 over 1. So it's going to go like that. That's going to be its guideline as it goes right and left forever. So the graph will do I don't know whatever and eventually approach that line. That's what we discovered. Is that good? That's how you find diagonal asymptote lines. Long divide the bottom into the top. So when do you get a diagonal asymptote line? Whenever the top is 1 power more than the bottom. Because you're going to get an mx plus b then, and you find it by turning it in, by long dividing, turning it into an improper polynomial. I mean a mixed polynomial. It was improper. All right, that's probably more. So this is the last part of number 6 here. Here's the end. Is they want you to get the actual graph. Just use your calculator. Just type it into your calculator and hit the graph button. But I want you to see how they all have those diagonal lines they're headed off to. I just wanted you to see what it really looks like in the end. Can you tell which, actually there's a way you can tell which one of those is right without even a graphing calculator.
Equals the vert is going to be at 6.
Remember it was x plus 8, the diagonal asymptote.
Yeah, but the vertical asymptote is going to be at 6.
Oh yeah, the vertical was at 6, positive 6, yeah. Good.
So C, I would think, no, maybe.
Yeah, it's got to be C. Does everybody see that? Because especially the diagonal asymptote, this has got to be a positive slope, right? This is 1 over 1 positive slope. So the dotted line's got, the diagonal dotted line has got to be going up to the right, not down. See how A is going down? See how the dotted diagonal line in A goes down and D goes down? No way. And now, so B, the dotted line goes up. But see how its y-intercept is wrong? The y-intercept is supposed to be up at 8. See how this one's up above the origin, whereas this one's y-intercept is below the origin? So that's why it's got to be C. So there's what the graph really looks like. See how it follows the vertical asymptote
With B,
and the two diagonal.
vertical asymptote's at negative.
Oh, that too. It's got double problems, yeah. Is everybody good on that? So see what all these asymptotes actually do on a graph eventually? The graphs hug those lines eventually. All right. Okay, well, yeah, this is a pretty ugly one. Really, it's a factoring problem. We don't have a lot of time because there's 3 big word problems at the end of this section that I want to do a good job on with you. So I'm going to go fast on this. So you really need to the trick on this one is it needs to be factored. Number 8, make note of it for your homework. Number 8 needs to be factored and something's going to cancel, it turns out, when we factor. So to factor, I just look at that 30 and I think 5 times 6 is 30. So 5x, 6x, either order, you can put the 6 first, then the 5, doesn't matter. And then I look at the 56 and I go, what times what's 56?
8 times 7.
7 times 8. If you're rusty on some times tables, use your calculator. 7 times 8. Now, do you all know the trick? So I'm going to do 7 and 8. Catch this. This will help you in your factoring. Did you know the 8 cannot be there? It cannot be in the same parenthesis with the 6. No way. No way. Why not? Why can the 8 not be in the same parenthesis with the 6? Do you remember that from your algebra days? Because they have 2 in common. You could take out a 2. If there was an 8 in there with a 6, they would have 2 in common, and then you could take out the 2. So what? Why is that the end of the world? There can't be a 2 in common. Why not? I would have seen it back here in the beginning. They didn't all have 2 in common from the beginning, so how could they have 2 in common later? They cannot. Do you see that? You take out any commonness right in the beginning. That way, when you get to the double parentheses, you know there's no commonness left. So that speeds you up. That helps you. Then you go, well, the 8's not there. The 8 must be over here with the 5, because the 5 and 8 have nothing in common. And the 7 must be there, because 6 and 7 have nothing in common. Do y'all see that? It helps you speed up and eliminate some possibilities quickly. So then, is that right? That actually is. Yeah. You can FOIL it out and see. I'm just looking in my head and saying that's 48 and that's 35. I'm imagining the FOIL. I've FOILed tons of times, and so I can kind of see what's going to happen. And I want that one to be negative and that one to be positive to make minus 13 in the middle. So that's negative and that's positive. So anyway, just FOIL, and you'll see that's right. And then on the bottom, same kind of thing. 5x squared, so I'm thinking 5x and regular x. 72, what times what's 72?
8 and 9.
8 and 9. If I put the 9 here and the 8 there, it's not right. How do we know? Because, I mean, it's okay as far as 5 and 9 have nothing in common and x and 8 have nothing in common. But these two make 9, these two make 40. 40 and 9 are never going to make negative 53. So then I swap the order. The other order's acceptable also. Now the two middle make 8 and the two out make 45. 45 and 8, yeah, that'll do my 53. Both negative, and two negatives make positive 72. There it is. So again, FOIL as you need to make sure. But see how we got a match now? These drop out, don't they? That's the trick of this one. So it becomes 6x plus 7 over x minus 9. So for the rest of the problem, just use that. Now, let's answer the question about domain.
Negative 8 times positive 7 is not positive 56.
Oh, did I miscopy the problem? Thank you. Yeah, it's supposed to be minus 56. Thank you, Renee. Yeah, the original was a minus 56. Thank you. So the domain, now, something, I know I'm saying a lot of things today that I'm saying focus in on this, but here we go again. Focus in on this, because this is kind of a weird thing that I got an email question just this morning before class that I answered from a sharp student who noticed this difference on this particular problem. And so let me say it for everybody. It's tricky because you think, well, the 5x minus 8s are gone, so they're gone. Well, they're sort of gone. They're sort of gone.
They're only sort of gone.
Yeah, like, what do you mean, Ms. Aaron? They're sort of gone. That's like weird. Right. The only place they're not gone for is domain. Domain everything in the original must, that's a kind of scribbling now, everything in the original must be used. So in other words, you've got to consider the fact that for a second there was a 5x minus 8 in that denominator. He's part of the issue for domain. I won't worry about him for anything else in the problem. After domain, I'll just go back to this and forget that there was ever those 5x minus 8s. Is this making sense? This is weird. It's weird that we have to use it in one part and not in other parts. That's what the student was noticing and emailed me, and he was sharp to notice it. That's exactly the issue. That why are we using the 5x minus 8 in one part, and then like we're not going to use it when we do the vertical asymptotes or anything else? Well, that is what we do, because it really was there. It really was there, right? I mean, we can't pretend it wasn't. It really was there for a second, which means it really is going to be a problem for the domain. Anything that would make that 0 will choke the function. You can't allow it. So, right, for domain, I'm stuttering here. For domain, you got to do denominator 0, don't you? So that means you do have to include the 5x minus 8 and the x minus 9. Both of them can't be 0.
So 9 8/5.
Yeah, so that is an issue. So the 8's got to jump over there, divide by 5, and the 9's got to jump over there. So both those are not allowed for the domain. But after this, but now that we've done that, I'm going to forget about those 5x minus 8s when it comes to the vertical. Now that's the part the student was asking about, like why? Why can we suddenly skip it? So when we go on to part B, and I find out what is the vertical asymptote for this function, I am only going to take the x minus 9. And I'm going to say x minus 9 is 0, move the 9 over, and you get 9. That's the only vertical asymptote. I do not use the 8/5. Why not? Well, because the 8/5 won't really make a vertical asymptote. He will not really make the bottom 0 long term because he cancels out. The 5x, I mean the 9 will, but the other one, the 8/5 will not, because that term drops out. What it turns out will happen there is it'll be a hole in the graph at 8/5. Right here, there's a hole in the graph. I'll show you the picture. In fact, let me just show you the picture right now. Yeah, you see, I don't know which one's the right graph, but see how they have those holes? See the hole there, and the hole there, and the hole there, and the hole there? They're all having that hole. That hole is the 8/5. Where is it? It's the 8/5, which is 1.6 on your calculator. So the hole is supposed to be at x is 1.6. So it's not A. Whoops, it's not A, because that's at negative something. It could be B, could be C. It's not D. See, the hole is left. It's not left. The hole, not the hole, I'm writing the wrong kind of hole. The hole is at x is 1.6. That's what 8/5 is if you divide in your calculator. 1 3/5, 1.6. So 1.6, it's one of those two. I don't really know which one. Well, I guess the horizontal asymptote would tell us, is it positive or negative horizontal? The horizontal would be positive 6. So it's C. It's always C. No. That's the right answer right there. The horizontal's up there at positive 6. So anyway, that's the real graph. So it's got a hole in the graph there at 8/5. It does not have a vertical. So why? It's not allowed in the domain. That's what we mean by the domain does not allow it, because it really was part of the original problem. So you really can't plug in 8/5. It'll make that bottom 0. But it's not a place that as you get close to, yeah, that's a better way for me to say it. I keep thinking, how do I explain this? It's probably because I'm having a little trouble completely grabbing it. I think I've got it now. Right there, it's not allowed. But as you get close to 8/5, it doesn't blow up or blow down or do anything special, because it drops out as you're close to it. It doesn't matter. That's why it doesn't blow up and blow down. It's not a vertical asymptote, because it doesn't do anything special as you're close to it. It only does something special when you're right on it. Right on it, yeah, it's a hole. But close to it, doesn't matter at all. These guys are out of there. So anyway, that's probably as much more time than I have for that. I'd love to talk more in my office hours. I can make up other examples and show you problems to do that. You're going to have that in calculus. They'll give you graphs with holes in them. So you do need to eventually understand why that happens and how that's different than a vertical. So I'd be glad to talk more about that with you in office hours. Let's finish up. Did you see how I got the horizontal asymptote on this one? Can I go back and do that? So let me just erase this and do the horizontal, and we'll be done with this tricky problem. So for the horizontal asymptote, so horizontal or diagonal, as the case may be, what do? You're letting x head to infinity, right, or left forever, wondering if it flattens out or diagonals out, or what does it do? All that matters is the most powerful term or most powerful term, huh? So it's going to be 30x squared over 5x squared, which is just 6. So that's a flat. There's no x there. That's a flat up at 6 horizontal asymptote. That's how I knew the answer was C, because it was up here, not down there.
Couldn't you take the factor after the 5x minus?
You could. Either one.
Yeah.
Either one would be fine.
The x's cancel, it leaves you 6.
Same thing.
Okay.
Either one will work fine. Good on that? Here, let me write it. Number 9, y equals x plus 2 over x. Basically, they're giving us this one in mixed number form. Mixed number polynomial format. They're not giving it as one big fraction. Do you see that? That makes sense? It's all right. I guess it's not the end of the world. It's just a different format. So let's do part A. What is the domain issue?
X cannot be 0.
Yeah, x can't be 0 because there's the denominator, huh? What's the vertical asymptote?
0.
Yeah, same thing. X is 0. Because as you get close to 0, that function is going to blow up and blow down. It's going to have vertical asymptote. C, what's the story with the horizontal diagonal asymptote?
Well, there's no x on top, so
Yeah, this is where
it'd be
it might be confusing.
1 over x.
It's really already in good format.
Yeah.
The answer is y equals x. It's diagonal, and it's y equals x. Look at it. Just look at that function for a minute. Look at that function. This is where understanding is better. Well, it always is better than rule memorization. If you understand, if you really get it, why this is happening and what the engine is that's driving this car, think about whenever they ask you about a horizontal or diagonal, you mean as it goes way off to the right or the left forever, what's going to happen? Well, as I take this function and I plug in like 1,000,000 here and here. What's going to happen to this piece? What's 2 over 1,000,000?
2 divided by 1,000,000.
If I said last night I had 2/1,000,000ths of the pie, that's headed to 0. This is just y equals x. We can just see it. Does that make sense? It's in the format that we usually get after log dividing. It's already there. Right? You with me? Let me go back. Let me go back and show you. Remember number 6? Remember that long, drawn-out number 6? Started like a big old improper fraction with the top being a bigger power than the bottom. And then we did our long division stuff, which right here, and we got it to look like that. You see how that's mixed number kind of format? With the x in the front, then the a? Right? They're giving it to us on this problem, number 9, already there. So you just say, yeah, as x goes to infinity, this part on the right is going to go to 0. 2 over 1,000,000, 2/1,000,000ths of the pie is just dust. It's gone. It's just y equals x, diagonal, asymptote, done.
X equals 0? Oh, it's a diagonal.
So I'm saying as you go off to the right forever,
Yes.
in what fashion will it go? Y equals x is all that matters. That x will stay. He matters. But this guy doesn't matter. Because he's 2 over 1,000,000. So that's what it'll look like as it heads to the right and left forever. So that's the diagonal line y equals x, huh? So I don't know what it'll do, in the middle. It'll do whatever it wants to do in the middle. Blah, 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 blah. But eventually it'll go there and go there. Let's look at the real graph. There we go. Okay. So this is the graphs for number 9. So which one's right? I don't know.
I think it's C.
C or D. It's not. See, the diagonal line's got to go up to the right. Remember it was y equals x. The diagonal asymptote line. So see how it's not B. That one's going down. Not A. That one's going down.
I was going to say, this isn't,
C or D.
it's positive, and 1 over x is 1 in the right and 1 in the bottom left.
Yeah, so I don't know. It'd have to be, yeah, you could plug in points. I better move on. Okay, so number 11 is just graphing utility. Put that in, y1 equals x plus 11 over x. Graph it on your calculator. They're telling you the window. See right here?
Oh, good.
That's the x min and x max. This is the y min, y max. And graph it, and then find the minimum. You know how to find the minimum. We went over that a couple weeks ago. So 11, 12, 13, they're all just like that. Just graph it on your calculator, find the minimum. They're kind of asking the question backwards. They're giving us the graph, and they're asking us which of those 4 functions could be that actual graph. So you can do this one, this kind of question. There's 1 or 2 of these on the next exam, exam 2, and they're in part 1 where you don't have your graphing calculator, because I want you to be able to do this without just typing it into your calculator. Just showing that you know how to do vertical and horizontal asymptotes. So just by looking at the asymptotes, really nothing else,
It can't be A or C.
you can figure out what's going on. Let's look at the vertical asymptote here,
It's got to be B or D.
and the vertical asymptote there. So where are those vertical asymptotes hitting?
5 and 9.
Minus 5 and 5. And what makes a vertical asymptote happen in a formula? Denominator, right? I've got to have in the denominator x minus 5 and x plus 5. That's what makes those verticals, right? Denominator 0 things. And so that means the bottom has got to be x squared minus 25. That's got plus, no way. Good so far? A and C are out. So it's either B or D. What do you think? Is it B or is it D?
One is negative, one is positive.
Look like same.
What's the only difference between B and D? They're pretty similar, huh?
Oh,
No negative.
yeah.
D has the negative and B doesn't.
It's going to be B because when the denominator and the numerator, the x to the second cancels out, and then it's 2, so the horizontal asymptote's going to be at 2.
I think it's not going to be D because coming down the problem.
So, so what we should look at is what Renee's saying, the horizontal asymptote. Because it's easy to get fooled, and they're trying to fool you with this U, and see how they put it down. They want you to grab that negative, but there's no such rule that says if there's a U somewhere going down, it's got to be negative. There's no such rule as that. So don't be fooled by that. Instead, just go after the horizontal asymptote. You know how to find the horizontal. What do? Most powerful term in the top, most powerful term in the bottom as you go off to the right and left forever, right? So it'd just be 2x squared over x, if it really is B. And then these would cancel. That's positive 2. That indeed is where the horizontal is. Positive 2. See, if it was this one, it'd be most powerful, and the negative. It'd be negative 2x squared over x squared. It'd cancel, it'd be negative. The horizontal would have to be down here, and it's not. So the answer is B. Everybody see that? The reason that U shape is down there negative, if you're interested, it's because if you plugged in like 1 or 2 or something like that, the bottom would be negative. Because 1 or 2 squared minus 25 is negative, and it's because of that, not because of a negative in the front. All right, so it's tricky, but just find the vertical and the horizontal asymptotes, and you can tell it's B. Does that make sense? We good there? Math gets real. So here we are. Here's a medical. So 4 real problems in a row. This is a medical problem. It's C of T. Concentration of a drug in your bloodstream is T over 7T squared plus 6.
The concentration at a certain time.
Yeah.
I have a chem exam tonight, so this is
All right.
This is going to screw me up.
So C of t equals t over 7t squared plus 6. All right, so that's the concentration at any time t.
Yeah.
So, how do we do it? How do we find the concentration of the drug? Well, first off, first question, they're gonna ask me about the horizontal asymptote. So where does that go? Where does the horizontal, how do we find, so you guys are pros now at the horizontal asymptote. So that means as we go right forever or left forever, what's the graph going to do? Flatten out or diagonal out, or what's it going to do? Well, so we plug in infinity, don't we? All that's going to matter is the most powerful term in the top and the most powerful term in the bottom. The plus 6, if you're plugging in infinity, isn't going to matter. So it's going to be t over 7t squared. The plus 6 doesn't matter. If you're plugging in infinity, right? This t will cancel that, and you'll get 1 over 7t. So far, so good? I'm just thinking about what's going to happen. They're asking me for a horizontal asymptote. That always means as you go right forever. As t, time, goes to infinity. We're wondering after infinite hours, what's going to happen in your bloodstream? So 1 over 7t, plug in the infinity, or the 10 million, or whatever you want. So it's going to equal 1 over 7 times, a million. So 1 over 7 million?
0.
Right. If I ate 1 7/millionth of the pie, that's no pie. So it's headed to 0, isn't it? Is that reality?
Yeah.
Yeah, if they give you some kind of drug in the hospital, right, it's going to peak out in your bloodstream, and then after enough time, your liver, right? You guys tell me. I'm not a medical expert at all. I believe it's your liver, right? Just like pulls it all out over enough time until eventually, after enough hours, enough time, as time goes to infinity, it just comes down to there's basically none of it in your bloodstream after enough time. Right? So that fits reality. So remember, all of math is just made. Why did they make up horizontal asymptotes? Well, because there's things in real life that behave with horizontal asymptotes. Math is made up to fit reality. So yeah. So then they ask you, hey, graph it, find the maximum. That's what they would care about in the medical world, is when is the amount of that drug in your bloodstream peaking? Like, what's the max here? After how many hours? After 1 hour, after 2 hours, after half an hour? When will it peak and then start going down? You just find the max on your calculator. We good with that? And how do you know they find max? They say so. Number 17. We're going to make a rectangle next to a river. We're going to make a rectangle next to a river.
Okay.
So in other words, it's like we're going to have a river, and then we're going to put in 3 sides, and then the river will serve to be like the 4th side to make a rectangle to hold some animals. And we'll put in 4 corner posts. That's the plan. So rectangle next to a river. Let me give you some more details here. The enclosed area, the area equals 1,000 square feet. So we need the space inside the rectangle to be 1,000 square feet. Give enough space for the critters. So
area equals rectangle.
And then we'll go on. The fencing for the side parallel to the river is $9 per foot. So the fencing parallel to the river is $9 per foot. So that's going to be this side over here, isn't it? See how that side, this goes parallel to the river?
Correct.
And then they're going to say the fencing perpendicular.
Which means it crosses it.
Perpendicular. It hits it like a T to the river is $2 per foot. I get that right? Yeah. So that means this fencing, and that fencing are $2 per foot.
Why is it different fencing?
Some of it has to go on the water. Some of it is, I don't know. All right, and then the final fact is the 4 corner posts are $35 each. Got to put in the 4 corner posts. So 4 corner posts, $35 each. So the question they have for us, basically in the end, we want to build this in the cheapest way possible. Cheapest possible way. What's the cheapest way that we can build this pen for the animals that's big enough, it holds 1,000 square feet, and yet it's as cheap as possible? Let's think about that for just a second. I think that'll, more real we can be with this, the more the details will make sense as we dive in. So just think about it with me. A lot of times it's really valuable to just play around with problems for a minute, but it takes time. But just as you get in a really difficult, real-life kind of problem, just to stop for a second and go like, what are they even talking about? Let me just think. So we have to have 1,000 square feet of area. Right? Got to have 1,000. There's a lot of ways you could do that, huh? Yeah. You could go like, I don't know, 50, 20, 50. You go 50, 50, 20. Why? Because 50 times 20, remember, that would give me 1,000 square foot area, wouldn't it? You okay there? The area. Remember, the area of a rectangle is just one side times the other, isn't it?
I think you should do 100 feet with the $2 and then 10 feet with it.
We'll try it. So, everybody good so far? I want to make sure this makes this area 50 times 20, 5 times 2 is 10, and then add on the 2 zeros. That does give me 1,000 square feet. That would provide area in the rectangle for the animals of 1,000 square foot. That's how we do area, right? Just one side times the other for a rectangle. So that would work. What would be the cost of that if we did it that way? What would be the cost? Well, this stuff up here is, what, $2 a foot? This is the cheaper fencing. And this stuff down here is $9 a foot, huh? So the cost would be 50 feet of fencing at $2 a foot. And then on the bottom, same thing, 50 feet of fencing at $2 a foot. And the right side would be 20 feet of fencing at $9. 100, 100, 180, 380. Plus the posts, but you got to do the posts no matter what. I'll just say that's the cost without the posts. So there's one option. Now, yeah, so how about if we say, like Renee was saying, maybe you should make it just go out 10. Right?
No.
Oh, no, more. Yeah, because the cheap stuff is the top and bottom. So make more of that, huh?
Yeah.
Yeah. Good. You're right, yeah. So make this like 100? Is that what you said?
Yeah. Oh, yeah, that's what you said.
So I don't have room to show it. But
yeah.
you're saying like 100 by 10, basically, right? Because that would be 1,000.
Yeah.
That'd be a funny looking pen.
Yeah.
But yeah, why not? I mean, if that stuff's cheaper, wouldn't that be a cheaper way to build the thing? So let's do it. So this stuff is $2 a foot. This stuff's $2 a foot. This stuff's $9 a foot.
Only the animals don't have room to turn around.
Yeah, whatever. They're animals.
Sorry.
100 times 2, 100 times 2, plus 10 times 9, right? So what's the cost?
$290.
$490.
Oh, $490. Oh.
It's actually a little more expensive.
Okay. Oh, that's $200.
So that's actually not a better option. But probably something in that idea is right. Maybe if we lowered it a little bit to like 80 by 80 by something. Anyway, I don't want to play around anymore, but you get the idea. I'll let the math, I'll let the variables do the rest. That's why we love letters in higher math. You see, the letters, when we put the letters in there, the letters will automatically try every number for me and give me the best answer that quick. That's what letters do for us, right? Otherwise, I'd be plugging in numbers forever. Okay, so you get the idea. So we're trying to do this in the cheapest way possible, giving 1,000 square foot of area for the animals, giving no consideration to anything else. Okay, so let's do it. So we have this fence. We're going to build it however we build it. Oh, and one thing I forgot. They say let x equal the sides perpendicular to the river. So x is the top and the bottom.
So it's 2x squared.
So, and then the right side, I'm just going to call that y because I need something there. So this is x, this is x. They specifically said let x be those sides. They didn't say anything about y, but I got to call the other side something. So I'll do y. Rachel. Yeah, they just said let x be the sides perpendicular to the river there. So, okay, so now what they ask me for the cost function. So can we write the total cost function if we do x feet of fencing on the top and the bottom, y feet of fencing on the right side? What's the total cost? Well, the stuff on the top again is $2 per foot, top and bottom, $2 per foot. The stuff on the right side is $9 per foot. So it's going to be 2x plus 2x plus 9y. Good so far? How are we doing? Right? Because if on the top you do x feet of fencing times $2 per foot, and on the bottom you do x feet of fencing times $2 per foot, and then on the right side 9 feet of fencing times y. I'm saying that backwards, aren't I? You get the idea, do you? It's x feet times $2 per foot, x feet times $2 per foot, y feet times $9 per foot. Plus, now we do need the 4 corner posts. 4 of those at $35 each. Question, comment?
Well, just more of a comment. Like, could we just put, like, parentheses 2x squared to just make it
Well,
smaller?
no, because you're adding them in.
Going to be 4x?
Yeah, but, like, if you're adding it, let's say it's still going to be 4x because 2x plus 2x is 4x.
Yeah.
4x, not 4x squared.
No, I didn't know. Okay, never mind.
Okay. Yeah, fine. If you just want to write 4x, that's totally good. Plus 9y, and that's 140.
That's what I meant the first time. I said it can't
Because I want to keep affiliating with area.
Okay, so we good to there? So there's a cost function with letters. There's a cost function with letters. Now, the only problem we have with this cost function, we do still have one problem remaining, is the same problem we had a couple weeks ago when we were doing that section with the distance problems. Remember those distance problems? Find the point that's closest to the origin on the curve and that kind of stuff. We don't want y in there. We want only x. And that's what they're going to do on all 3 of these. This is number 17 still. On 17, 18, and 19. By the way, let me just be straight up. One of these for sure will be on the next exam. I really like these. I think these are very valuable exercises. So every semester on exam 2, I put either 17, 18, or 19. I don't remember which one. I switch it around every semester. So it's one of those 3. So make sure you do a good job on 17, 18, and 19. Okay, so in all 3 of these, it's the same deal. You'll get your function at first like this, and it'll have y in it, and you got to get rid of the y because we want to get it down to only x. We don't want 2 letters because in a minute we're going to go to our graphing calculator and we only want to put in x, not y. So how do we get rid of that y?
Get it to the other side and then divide it by -9.
Need to use another formula to solve for y and substitute in. Substitute in for y right there. Does that make sense? We need to find another formula, solve for y, and substitute in. That's what you're going to do in all 3 of these problems. It's the same game. At first you have the x and the y formula, then you've got to go find some other fact in the words that you haven't used yet, and then plug that in. Let's go back to the words, and let's look for some piece of information that we've not used yet. There's only one. Do you see a piece of information in all those words that we've not used in our cost
We
formula?
know what x equals.
Area is 1,000 square feet. We've not used that yet in our cost formula. That's what we want to use.
That's why.
So go back and we say, okay, there it is. So area, maybe I'll create a little more room, put it over here. Area is 1,000 square feet. So now, how do you find the area? What's the area in this? That's the space in the middle, huh? Of the pin. How do you find the area of a rectangle?
Base times height.
One side times the other, called base and height, length and width, whatever you want to call it. One side times the other, x times y, huh? That makes sense? Area is x times y, which means it's 1,000. So 1,000 is x times y. Is that good? Because the area, x times y, is 1,000. I don't know, is that confusing the way I wrote it? Kind of funny. So the area, x times y, is 1,000. So now why am I doing that? What am I going to do with that? I'm going to solve for y and substitute in. That's why, so in all these problems, so I want to make sure this idea, get this idea, it's always the same, 17, 18, 19. You always have a second formula, which is kind of like a helper. It's going to help us make the main equation only have one letter. Get the idea? This is the helper over here, the secondary formula that's going to help us make the main formula only have one letter. You solve for y.
So y is 1,000 over x?
Yeah, divide by x, exactly. So y is 1,000 over x, and then grab that and plug it in. So grab that 1,000 over x and plug it in right there for y. So what are we going to have then? We're going to have cost equals, right here, let me change the color a little bit. Four x plus 9 times y, and what is y? 1,000 over x plus 140. We good to there so far? So we have a cost formula now that has only x, huh? Let's simplify that a little bit. So that'll be 4x plus, what do you do when you have a whole number multiplying a fraction? It's 9 over 1, huh? It goes only to the top. 9,000 over x plus 140. There we go. There's a cost formula with just x. They'll ask you for one of the first questions they're going to ask you for. I think that's the answer to part A. Part B, they'll say, what's the domain of that thing? So what's the domain of that cost function?
X cannot be 0.
Yeah, I know we look at it mathematically and we say x cannot be 0. And that's true, but there's more than that that's also true in the real world. So whenever you're doing a real world problem, in math, you always want to keep one foot in the math world and the other foot in the real world. So yes, in the math world, x can't be 0 because that's the denominator. You can't make the denominator 0. But then look up there and remember, keep your other foot in the real world. Remember, in the real world, what does x represent? X is how wide these sides are. So could x be negative?
No.
So not only can x not be 0, of course it can't be 0. X can't be negative. You can't measure a desk or something and go, it came out -3. It's just weird. It can't be, right? So what they're going to say is x is greater than 0. It's got to be a positive. So that means it can't equal 0. That does include what we observed mathematically. Yes, it can't equal 0, but not only that, it can't be less than 0. It must be greater than 0. So that's because of the reality, not just because of the math. Got to keep one foot in reality. And then in part C, they'll say, all right, find the cheapest way to build that pin. We've come all this way. I normally, at this point, just say graph it, but let's do it. You guys got your calculator? Put that in for Y1. Hit the buttons. Let's find the best way to build that pin. I'm probably going to use up all of our time. We'll go quick. 4x plus 9,000. Whoops, I'm going too quick for my pen.
We only have one homework due on Tuesday?
Mm-hmm. 9,000 over x plus.
5 days
Are
to
you
do
going to have us graph this too?
40. Yeah, so you got to graph it
It's going to be one of the graphing calculator questions.
and find the minimum. Find the minimum. Okay. Oh, and they give you the window on this, which is very nice. Very nice of them. What do they tell you? There it is. 0 to 500, 0 to 1,000.
Wow.
So graph 0 to 500, for the x and 0 to 1,000 for the y. So that's the y min, y max, x min, x max. There's your window. So put that in for y1, set your window like they say, and we'll get an answer. In fact, I'm just going to go back and tell which one. My graph basically ended up looking like this. You get that? Oh, what did I do? Hit the wrong button. Did you get that? That's what I got when I graphed it. And not at first. I accidentally I got nothing because I typed something in wrong. So check your y1, make sure it's correct, and then your window is set correct, and you should get that graph right there. And then we want to find this point right here. That's the minimum. So you know how to do that? Go to second calc, go down to minimum,
That's what
go
x is going to equal, right?
left of it, right of it. And that'll tell us the x and the y. Where am I? I can't find where I am at all. Oh, I'm way too big. I looked at my x values. I'm in the hundreds. So I'm going to back up. There we go. Okay, boom, boom, boom. I'm getting x is 47.43 whatever.
Feet.
Y, yeah, feet. Y is 519.47. You getting those answers? For the minimum?
That's how many feet of each that we should be doing?
Good question. What's y? What's x?
That's the amount of feet for the $2.
So if we go back to the picture, look right here. X is the side, the sides that come out of the river. And y, well, hold on. Y on my picture is the other side. But remember the lesson we learned? Did you learn that lesson? Whenever you, from 2 weeks ago, whenever you put y1 into your calculator, that's the y it's graphing on your screen. What is that? That's cost. Remember, that's the cost function. This is the cost. This isn't the other side. Well, how do we find the other side? Plug this x into the formula.
Okay.
Makes sense? The cost is $519.47. That's what it's going to cost to build that. It's the cheapest pen you can build for the animals that will cover what you need. Hey, I thought we came up with a cheaper one. We didn't put in the posts.
Oh.
Yeah, go back to the posts. Yeah, where was that? There. Yeah, so if we add the posts into these, the posts were $140, 435s. That'd be $520. That's close. Wait, is that right? 520. This one, if you add the posts in, 140, it'd be 630.
Wow.
So 520, this is barely cheaper. And it is close, 47 feet instead of 40, instead of 50.
53
Yeah,
cents.
53 cents.
Oh my gosh.
So, everybody good there? So this is the x. How do you find the y? If you wanted to, they will ask you for the two sides. So this is the one side x. To find the other side, we had y right here. Y is 1,000 over x. So you go back and go, okay, to find y, the y being the other side, this y is cost. The y, the other side y is 1,000 over x. So it's 1,000 over the 47.43, whatever that is. I got to move on. Okay, so number 18. They're giving me a big old box. And parcel delivery wants to deliver a box. Volume's 8,500 cubic inches. What's the cheapest way they could build the box? With the least side material. That's what this problem is all about. Very, very practical. People that need shipping companies that need to ship things, especially if it's made out of, if it's got to hold something, like a gas or a dangerous chemical, and so the sides have to be a thick, expensive material. They're going to want to do it as cheap as possible. If they ship thousands of these, that's big dollars to them. They do hire math science people to calculate for them the kinds of shipping containers they should build. So that's what we're going to basically do. We're getting very practical at this point. So, surface area. So we need to start with the area of that big box. It's got 6 sides. So I'm just going to, and they're all rectangles. So I'm just going to add up the 6 sides. So S of x.
They're not all the same.
They're not all the same. Yeah, this is x, and y. So the height is different than the 2 on the bottom are the same. It's a square on the bottom. Square base. But the side is y. The height, in other words, is different. So bottom. What's the area of the, so we're going to have the bottom and the top. Then we're going to have the right and the left. And then we're going to have the front and the back. 6 sides. So what's the formula for the area of the bottom? Here's the bottom. What's the area of that bottom? How do you find the area of a rectangle? One side times the other. So x times x, x squared. Good so far? What's the area of the top? Same thing. Top and bottom are the same. Another x squared. What's the area? So we got the top and bottom. What's the area of the right side?
X squared.
X,
X times y.
by y. Everybody see that little y there? That one's going to be x by y. What's the left side? Same thing. So here I'm running out of room. Plus x times y. And now, all we got left, those are 4 of the sides. We got 2 left. What's the front? Yeah, the height is still y, just like that y back there, and the bottom is still x. It's xy, and the back is also xy.
2x squared.
So putting it all together, 2x squared plus 4xy.
Oh, 4xy.
Except, we don't want,
X times y equals 8,500.
we don't want the y. So we've got to do something about the y. We good there? Same problem we had last time. And so what other formula have we not used? What other fact? Volume is 8,500. Volume, that's the helper. That's the other formula which will help us do the main one. Volume, now what's the volume of a 3-dimensional shape? Length times width times height. So that's x times y. The volume is what? 8,500 is x squared y. Everybody see that? Volume is the 3 sides. So what are we supposed to do? Just what we did last time. Solve for y, plug it, substitute it into the main. So solve for y, divide by x squared. So there's y, plug it in for y right there. So what do we get? 2x squared plus 4x times y, and y is 8,400 over x squared. Can you all see that okay? It's getting a little messy. So 2x squared plus 4x times 8,500 over x squared. Let me bring that over. So the surface area, again, was 2x squared plus 4xy, and we had 8,500 volume is length, width, height, x, y. So divide by x squared and plug that in for y. So the surface area ends up being 2x squared plus 4x times y. And what's y? 8,500 over x squared. How do we simplify that? Anytime a whole number is interacting with a fraction, over 1, cross cancel, leaves x to the 1. So it's 2x squared. 4 times 8,500, 32 into 34,000 over x. There's the surface area formula. So the rest is the same. Plug it into your calculator, graph it, find the cheapest box, find the minimum surface area. Y1, graph, find the minimum. Find the cheapest way to build that container. Let's do one more. tubes, because this is a big problem, which I don't have time for. So basically, if you have a soda can, we're going to basically try to find the cheapest way to build the soda can to hold the volume we need, 500 cubic centimeters. So basically, if you have a soda can, imagine this is like a soda can I'm holding in my hand. It's technically called a right circular cylinder. That's the math word for a soda can shape. So if we have this, the top is a circle and the bottom is a circle. We're talking about surface area, right? Outside, top of circle, bottom of circle. That's pi r squared, area of a circle. And if you cut this open, the sides become a rectangle, don't they? The sides are a rectangle. Well, how do you fit into a rectangle, the sides? So we have a circle, and a rectangle like it's showing in the picture there. And what's the area of that? So the circles are pi r squared. How do you figure out the area of that rectangle? The area of a rectangle is width times length. Well, that length is height. It's the original height of the soda can. Just becomes the height of the rectangle. But what is the width? Where do they get that width? It was how far around the outer edge of the original circle. Opens up to become width, doesn't it?
Right.
What's the formula for how far around the outer edge of a circle? 2 pi r. It's the same thing as pi r squared. See it right there? 2 pi r, and they throw on the h. Because this is h, and this width is 2 pi r.
It's the same thing as pi r squared?
It's the same 3 letters, but the 2 comes in the front. Yeah, so, yeah, I'm out of time. I'm going to have to stop there. Look at other YouTubes to get more help with that problem.